Welcome to the 6.1 lecture on the law of sines. I'm in the room here today by myself, so I'll try to keep it as clear as possible and make sure that I explain everything well, since I don't have anybody to bounce my work off of and make sure that they're understanding. So we'll go ahead and move forward. Okay, so the objectives for this particular section are to first learn the law of sines and how to use it to solve oblique triangles. We'll also define what an oblique triangle is. We'll use the law of sines to solve, if possible, triangles or triangles in the ambiguous case. We'll find the area of an oblique triangle using sine function, and then we'll look at one application problem having to do with forest fires. Okay, so first thing is the definition of an oblique triangle. An oblique, that's O-B-L-I-Q-U-E, an oblique triangle is a triangle that does not contain a right angle. So they look a little on the skewed side, if you will. An oblique triangle has either three acute angles, or it has, which this would be an example of three acute angles, or two acute angles and an obtuse angle, which that example right down there shows one obtuse angle with two acute. So these are the only two cases that you're going to have for an oblique triangle. The relationships among the sides of the relationships among the sides and angles of right triangles defined by the trigonometric functions that we've already talked about. I'm going to point this out. They are not valid for oblique triangles. If you recall from all the other work we've done with triangles, we had to start out with the right triangle, and that's what we built our knowledge of the trigonometric functions on. So this is an alternative to that for when you're dealing with triangles that are oblique. Okay, so here's the law of sines for us. So we start out with the premise that A, capital B, and capital C are going to stand for the measures of the interior angles of a triangle. And little a, little b, and little c are the side lengths that are opposite of those angles. So if you just look down here at the diagram, I have angle C being noted by uppercase C, and then the side immediately across from that angle is lowercase c. So this is how you name your triangles. And we're given that when I divide a side by the sine of the angle corresponding to that side, that we have this, this proportion set up. So A over sine of A is equal to B over sine of B equals C over sine of C. So the ratio of the length of the side of any triangle to the sine of the angle opposite that side is the same for all three sides of the triangle. And I thought it would be beneficial to see how we get this law of sines here. So I'm just going to do a little bit, well, it's not a formal proof, but it's a little bit of a proof for you here. So if we start with this acute triangle ABC, and I drop a plumb line, if you will. Let me get a different color here. I drop a line from the vertex at angle C perpendicularly down to the opposite side, you can see that I form two triangles now. And so I'm going to give that point where my height of my triangle meets that side. We'll call that point D. So now I can name two triangles here. I have triangle ACD, and I have triangle BCD. And it doesn't matter the order that you name your triangles in. Normally we go in alphabetical order, but certainly it doesn't cause it to be incorrect if you don't name it in alphabetical order like that. And let me just remind you from our previous lessons that the sine of theta is equal to the opposite over the hypotenuse. So if we take case for angle A and B, according to our sine function here, the sine of A would be equal to the hypotenuse. That's going to be the opposite side of the angle there. The hypotenuse over B. I'm sorry, the opposite. My bad. Let me start over and point this stuff out because I'm losing myself in all this afternoon. Once again, I'm coming from being on the go since 4 a.m. this morning, and this is the third lecture I've given today, so I'm a little pooped at this point. I'll try to make it through and have it be understandable. Okay, so let me get a nice bright color here, orange. So I'm going to start out with the sine of A. So that's this angle right here. So that's the smaller triangle that we're looking at. The opposite of A is H, which is the height of our triangle. And the hypotenuse of that smaller triangle is actually side B. So I have that the sine of angle A is equal to H over B. Now, if I start rearranging this and solve for H, which is my height, I can get an expression that represents the height there. So to do so, I would just need to multiply both sides of my equation by B to get it out of the denominator there. And I'm left with that H is equal to B times the sine of A. Now, if we look at the case for the sine of angle B, now I'm talking about the bigger triangle in my picture here. So here's angle B. The opposite, the side that is opposite angle B is side H, or the height of my triangle. And then the hypotenuse of my bigger triangle is actually A. So if I go and I plug that in, I have H over A. And if I want to solve for H there, I'd multiply both sides by A, and I end up with A sine of B is also equal to H. Now here's the part where you have to be clever. Notice I've named H here and I've named it here. And I've named it two different things, but since those are both equal to H, I can now say that A sine, I'm sorry, let me keep consistent with the sides of my triangle, or the sides of my work here. B sine of A is equal to A sine of B, because they're both equal to H. All right, so if I want to get this thing now looking like what I have going on up here between these two, I would need to just divide both sides by sine A sine B. And that's perfectly legal because I'm doing the same thing to both sides of the equation. There's no magic happening here. So my sine A's divide out on this side, my sine B's divide out on that side, and I'm finally left with B over the sine of B is equal to A over the sine of A. And I could continue that with all pairs of this proportion up top here. So I can say that these ratios of the side length divided by its corresponding opposite angle is always going to be equal or in proportion to another side length and the sine of its opposite angle as well. So that's how we get the law of sines. Now let's see how we can use it. Okay, so solving an oblique triangle means that you're going to find all of the side lengths and all of the angle measurements. That's what solving a triangle is. The law of sines can be used to solve these triangles where one side and two angles are known. And those three known measurements can be given by the acronym SAA for side, angle, angle. So I have one side and two angles. Or I can do it with two angles and the side between them. And we know this as angle, side, angle. So these are the two cases where we can use this law of sines here. So let's take a look at this example. Now this is a side angle angle example that we're going to look at. And notice we have the angle 64 degrees, angle A, and I've got angle C, which is 82 degrees, and I know one other side, which is 14, or side C there. So I have side angle, angle, SAA there. All right, so finding the third angle when you're given two is super simple. All you have to know is that the interior angles of a triangle add up to 180 degrees. So I have the formula, the measurement of angle A plus the measurement of angle B plus the measurement of angle C has to equal 180. I know A, which is 64. I don't know B, but I do know C, which is 82. And that all equals 180. And when I add 64 and 82, I get 146 equals 180. And then all I have to do is subtract that 146 off of both sides. And I find that the measurement of angle B is 34 degrees. So I'm going to go ahead and fill that information in that we know. So I know now that this angle is 34 degrees. So I have all the interior angles. Now I just need to use my law of sines, which relates my side lengths to my angles to figure out what the lengths of side B and side A are. And since I know side C and I know angle C, I'm going to use to find the side length of angle A, I'm going to use the proportion that A over the sine of A is equal to C over the sine of C, because I have my information for side C and angle C, and I've got my information for angle A, so I will be solving this particular equation for side A. So whenever you're choosing which ones to use, you want to obviously work with the one that you're looking for, but then you want to work with one that you know all of the information for. All right, so just solving for the formula itself, solving for the side A itself without putting any of the values in yet, all I do is multiply both sides by the sine of A. And those divide out on that side, and I have that A is equal to C sine of A over the sine of C. And now when I plug my known values in, I have that A is equal to 14 times the sine of 64 degrees. By the way, make sure your calculator is in degrees, not in radians. You always want to be very careful to check that before you get going. And that's divided by the sine of 82 degrees. So all I've done is plugged in my information. And when I put this into my calculator, by the way, it says round the side lengths to the nearest tenth, I get that side length A is approximately 12.7 centimeters is my measurement. So let me fill in that information on my triangle. I now know that this is approximately 12.7 centimeters. So the only thing I have left to do is solve for side B. And I can do it the same way I solved for side A, except I'm just going to use the proportion B divided by the sine of B is equal to C divided by the sine of C. Okay, so if I multiply both sides by the sine of B, just like I did above there, I get that B is equal to C sine of B divided by the sine of C. And plugging the values in here, I get that B is equal to 14 times the sine of 34 degrees divided by the sine of 82 degrees. And when I put that into my calculator, I get that B is approximately 7.4 centimeters. So I'll just add that to my triangle off to the left here. So B is approximately 7.4 centimeters, and my triangle is solved for. I have all three interior angle measurements, all three side lengths. Okay, now we're going to look at a case for an angle side angle. So before we get going, let's label this triangle. We have that angle A has a measurement of 40 degrees, and we're told angle C has a measurement of 22.5 degrees. So I have a side of 12 and an angle of 22.5. And we're basically going to do the same process for this triangle that we did for the last one. The first thing we're going to do is find that last interior angle measurement. So the measure of angle A plus the measure of angle B plus the measure of angle C has to total 180 degrees. So that is 40 plus B plus 22.5 equals 180. And when I add 40 and 22.5, I get 62.5 plus B equals 180. I subtract 62.5 off of both sides, and I'm left with B is 117.5 degrees. So I'm going to go ahead and fill that in on my triangle. I now know that angle B is 117.5 degrees. Now I have left to figure out what is the measurement of side A and what is the measurement of side B. I have the measurement of side C as 12. So I'm going to use my law of sines to do so. So I'll look for A first, and I actually, oh goodness, I mislabeled my triangle. I put side C over here. This is side B right here, and this is side C. And this is why I need Roy catching all my little craziness here. So B equals 12 and C we are looking for. So we know all of our information about angle B and side B. So that's the part of the law of sines that I'm going to use to find my side length of A and my side length of B. So I first start out with B over the sine of B is equal to A over the sine of A. I'm trying to solve for the sine of A again. I'm not going to go through all of the business because I just did this on the last slide, but we get that A is equal to B times the sine of A divided by the sine of B. And when I plug in values, I have A equals 12 times the sine of 40 degrees over the sine of 117.5 degrees. And when I put that into my calculator, A comes out to be approximately 8.7. So now I know that the side length A is 8.7, and they didn't give us a particular type of measurement like feet or centimeters, so we'll just call it 8.7 units. And now looking for side C, so now this time I want to set up B over the sine of B is equal to C over the sine of C, and when I multiply both sides by the sine of C, I end up with C equals B times the sine of C divided by the sine of B. All right, plugging in my information, I have C is equal to 12 times the sine of 22.5 degrees divided by the sine of 117.5 degrees. And when I put that into my calculator, I get that C is approximately 5.2. So C is 5.2, and my triangle is now solved for. I have all three interior angles and all three side lengths. Okay, so now we have the ambiguous case. So let me just remind you, our first two cases where we were able to use the law of sines easily, we had angle, angle, side, and we had side, angle, side. So the one that we have left is the ambiguous case, side, side, angle. And when I used to teach high school, I'd make them giggle, but it also helped them remember the one that was different by saying, this is the ass case. Angle, side, side is the weird one. So if we're given two sides and an angle opposite of one of the two sides, the given information may result in either one triangle, two triangles, or no triangle at all. So that's why it's called the ambiguous case, because when you start out, you're not sure what you're looking for until you start pulling some values out of the process. We'll go ahead and move forward, and I'll explain a little bit more as to what this diagram right here is showing us. Okay, so here are the cases that could be possible. Okay, and let me redraw that diagram from the last page. So we had this happening. That's a perpendicular line dropping down. So we're calling this angle A, which means the side opposite is side A. And then we have side B. This is H dropping down here to potentially be, I'm sorry, let me back up with my drawing. I don't know if I have an eraser feature. I don't think I do. I'm going to have to redraw that whole thing. Let's just do this and start over. Okay. No harm, no foul. It's the beauty of technology. Okay. So I have, and use your imagination. Okay, so here's the height dropping down perpendicularly. So that's H. Here we have angle A. That makes this little piece side A. There we go. And this side B. So we have an angle, a side, and a side length that we know. Okay, so here's the problem with this. If side A is greater than H, which is that perpendicular line, it's the height of the triangle. If side A is greater than H and A is greater than B, then we have one triangle that's formed here. So here's our H, and you can see side A is greater than H, and it's greater than B. That's going to form one triangle for us. If side A is equal to side H, it's going to drop down right along with side H. That's going to form one right triangle for you. Now here's the tricky one. If side A is less than side H, it is not long enough to form a triangle. So here's our hypothetical H, and you can see that side A cuts off there. So even if I pushed it out here, it's not going to form a triangle. That's this picture right here. There's no triangle that can be formed with that. And then we have the case of two triangles. That's when A is greater than H, but A is less than B. You're going to have two ways. Here's our H dropping down. You're going to have two ways that triangle could be formed. So we'll move forward and look at a case of no triangle being formed, and we'll look at the case of two triangles being formed. Okay, so this is an example of no solution. So no triangle gets formed in this particular example. Well, let's take a look. All right, so I'm just gonna draw our little picture here. Okay, so here is angle A, here's side B, and here's our potential side A, or there's our side A. Our height, I'm just going to draw this out here. Our height is given by if you draw a line down perpendicularly to its opposite side. So this is representative of the height right there. Okay, so let's take a look at this case. We are given that angle A, let me get a different color here. Angle A is 50 degrees, so we know that. We know that side A is 10 degrees, 10, whatever measurement, and side B is 20. Okay, so we have an angle, a side, and a side. So I'm going to use this version of the law of sines here. And actually we can, before we start using the law of sines, we can figure out angle B. No, I'm sorry. That's what we're going to try to figure out. I was looking at the wrong side of my paper. Let's go ahead and start with the law of sines. So we have A over the sine of A is equal to B over the sine of B. All right, and when I rearrange this to solve for the sine of B, because I'm trying to figure out that angle here, it's going to tell me how A approaches that opposite side there. Side A approaches that opposite side. So I'm going to solve this equation for the sine of B. And to do that, I multiply both sides by sine of B and the sine of A. Same thing over here, sine, didn't leave myself too much room, sine of B, sine of A. So here's what happens when I do that. I have sine of B divides with sine of B, and sine of A divides with sine of A. So at this point, here's what I have happening. A times the sine of B equals B times the sine of A. And then I just need to divide both sides by A to get the sine of B by itself. And that leaves me with the sine of angle B is equal to B times the sine of angle A divided by sine A. So when I plug my numbers in here, I get the sine of B is equal to 20, my side B, times the sine of 50 degrees, my known angle, divided by 10, my side A. And when I put that into my calculator, I get the sine of B is equal to 1.53. Well, if you think back to your unit circle, the sine of an angle is equivalent to its y coordinate. There is no y coordinate within the unit circle that's greater than 1. So when I go to solve this by using the inverse sign, you're going to get a domain error. So if I put into my calculator the inverse sign of 1.53, I should get the measurement of angle B out. But because that right there is undefined, then I get domain error. So let me outline this in red. And what that tells you is that there is no angle B for which the sine is greater than 1. In other words, there is no triangle that exists with these measurements. All right, so this right here can't happen. All right, so another ambiguous case with side-side angle. Whoa, I went one too far. Let me go back. Okay, with side-side angle. Okay, so for this particular one, we are given, let me just draw my little diagram again. Okay, we're given that angle A is 35 degrees, side B is equal to 16, and side A is equal to 12. I could probably extend that out a little bit more. And then I have my height dropping down. All right, so let's go ahead and move forward with this. So once again, I have the same information that I had with the last one, so I'm going to use the same law of sines. A over the sine of A is equal to B over the sine of B. And manipulating that just like I did with the last one to solve for the sine of B, I get that the sine of B is equal to B sine of A divided by side A. And when I plug that in, I get the sine of B is equal to 16 times the sine of 35 degrees over 12. And when I put that into my calculator, I get approximately 0.7648. Now, if we think about the unit circle, use your imagination on the circle there. I have a y value of 7.68. I'm just going to dot in y equals 7.68 there. I have a y value, which is the sine of the angle. I have one in quadrant 2, and I have one in quadrant 1 there. So when I take the inverse sine of 0.7648, I get approximately 50 degrees. So there is an angle here that's 50 degrees, but if I subtract 50 degrees from 180 and have that other one there, I get that I could also potentially have a 130 degree angle. So I could either be talking about, let me outline this in green for you. I could either be talking about this angle that's 50 degrees, or I have the same phenomenon with this 130 degree angle. So let me just put that onto the screen formally. We'll just call angle B sub 1, because we have two possibilities, 50 degrees. And B2 is going to be 180 degrees minus the 50 degrees, which is 130 degrees. And when I want to figure out what my angle C is, I have two possibilities for angle B, so I've got to have two cases for angles C, angle C1 and C2, that go along with B1 and B2. So there are two possibilities happening here. And just to point out, angle A plus angle B1 is 35 plus 50, so that's 85 degrees. And angle A plus angle B2 is 35 plus 130, which is 165, 165 degrees. So I have those two possibilities that are still less than 180 degrees. And the reason that I'm fixating on 180 degrees is because that is the sum of the interior angles of the triangle. So I've got two possibilities happening here. So I'm going to move to a clean page and we'll work with both of these cases. Okay, so let me just rewrite some of the information from the last page that we're going to need to move forward. Okay, so we have B1, which is 50 degrees, and then I'll have a B2 case, which is 130 degrees. All right, so if I want to find my angle C here, I have angle A plus angle B1 plus angle C1 has to equal 180 degrees. That's 35 plus 50 plus C1 is equal to 180 degrees, and that's 85 plus C1 equal to 180. Subtract 85 from both sides, and I get that angle C1 is equal to 95 degrees. Okay, and continuing with this case, if C is equal to 95 degrees, then I have that C1, this is little c, let me make that smaller looking so that we know we're looking for side length C. And I'm not going to derive this version of the formula because I've done it quite a few times already in this lecture. So if you're not sure how I got this, just go back and rearrange that. So little c1 side C is equal to side B times the sine of angle C1 divided by the sine of angle B1. So once again, if you're not sure about that formula and how I got it, Just set up your law of sines proportion and solve for C. All right, so when I plug the values in here, I get 16 times the sine of 95 degrees divided by the sine of 50 degrees in this case. And this gives me a side C length of 20.8. Right. So that's our first case. The second case is, well, what if V is actually equal to 130 degrees? So I start the same way, A plus this time angle B2 plus angle C2 has got to equal 180. That's 35 plus 130 plus C2 equals 180. That's 165 plus C2 equals 180. Subtract 165 from both sides, and I get that angle C2 is equal to 15 degrees in this case. And now trying to figure out side length C, I have side C2 equal to B times the sine of angle C2 over the sine of angle B2. Plugging in, that's 16 times the sine of 15 degrees divided by the sine of 130 degrees, and I get approximately 5.4. So if we go back to that original drawing, here's what has happened. We have angle A here that's 35 degrees, and we were given that side B is 16, and side A is 12. So, given that information that side A is 12, let me drop our height down here. This is our height. I can have that side A either falls at a 50-degree angle to side B, or it falls at a 130-degree angle to side B. And both of these sides are 12. That's how the two different triangles happen there. And that's it. Okay, now let's move into talking about the area of an oblique triangle. So I'm sure that you have known since probably elementary school that the formula for the area of a triangle is given by, let me get a black pen here, is given by, let's see, the area of a triangle is given by 1/2 base times height. And we have back when we, on our first page of our notes, we found out that when we were deriving the law of sines formula, we had that H is equal to A sine B, or H is equal to B sine A, and then we could do the same thing with C's and stuff like that. But we'll just take the case of A sine B here, and then it applies to the other ones as well. So if our height is equal to A times the sine of B, then I could replace the H in my area formula with A times the sine of B. And the B in the regular formula doesn't stand for side B, this stands for the base. And the base is always given by the length of the side that is opposite the angle that you dropped the perpendicular line down from. So in this case, my B is equal to C. So let me just, or my base is equal to my C. So the area of this triangle can be given by 1/2 C, that's the base of my triangle, times H, which I already know is given by A sine B. And then as mathematicians, we like to have things in alphabetical order. So I end up with the area of the triangle being given by 1/2 A times C sine of B. So that's where this one, where is it? Here it is. That's where this one comes from. And the other ones follow the same sort of logic. You just flip-flop your sides around, drop it. In other words, you're dropping your perpendicular line from opposite sides. And then we have this one here. It's hard to do that diagonally to the side. So, follows the same logic the whole way around. Now let's use this. This is a pretty simple formula to use. Okay, so we want to find the area of this triangle. I'm given angle C here, and I'm given side B, and I'm given side A. And I want the area of this. So since I'm given side A and B and the included angle C, I'm going to use the form of the formula area equals 1/2 side A times side B times the sine of angle C. And now I just plug in my values and then put it into my calculator. 1/2 times 8 times 12 times the sine of 135 degrees. And when I put that into my calculator, I get that's approximately 34. This is given in meters, so it's square meters since we're talking about area. And that's it. Okay, our last problem is an application problem. So we have 2 fire lookout stations located here and here. And they are 13 miles apart. So I've already labeled that part of the diagram for us. In other words, our side C is equal to 13. Station B is directly east of Station A. Both stations spot a fire. The bearing, okay, so this is bringing back information that we learned quite a few sections ago, bearings. The bearing of the fire from Station A is north 35 degrees east. So this angle right here is north 35 degrees east. And if you're not sure about that, how I got that, you have to go back and look at the section talking about bearings. But I do know that if I have a perpendicular line to side C, that if that, and that perpendicular line comes from my compass here, how I listed my bearings, that means that this complementary angle has to be 55, because 55 plus 35 is 90. Same thing for the opposite. This is a bearing of north 49 degrees west. So that means a perpendicular, these lines are perpendicular, a right angle has been formed, which means that this interior angle has got to be 41 degrees. So now I have two interior angles and a side. Angle, side, angle. 55, 13, 41. So I can use my law of sines to figure out. The question is, how far is the fire from station B? So I'm trying to figure out what is the length of side A, because that's going to tell me how far it is from station B. So I want to use the part of the law of sines that relates my information for angle C, side C with side A and angle A. So I have C over the sine of C equaling A over the sine of A. And when I solve that equation for A, I get that A is equal to C sine of A divided by sine of C. And I need my C angle here, so I'll just use my formula for the interior angles. I have A plus B plus C equals 180. In this case, I have 55 plus 41 plus C equals 180. So 96 plus C is 180, which means C is 84. So now I know all my interior angles, and now I can plug everything I need into this function, into this equation to solve for the length of side A. So A is equal to 13 times the sine of 55 degrees divided by the sine of 84 degrees. And when I put that into my calculator, I get that A is approximately 11. So the fire is approximately 11 miles from station B. And that's all I have for you on the law of sines.